and this is the funky part actually. So when we talked about the autoencoder, and we were saying we might want to not use more layers, and this is fully connected, so I don't want to draw all the connections here.
Yeah.
So if you don't want to have an autoencoder learn a trivial function with this like larger hidden layer, then so you have x here and you want to get x hat. So you're like, there are two ways to do this, right? And so the first way is what we talked about in the class. So that's sparsity, and in the activations. So you force, or you learn that the neurons should basically suppress their outputs over time. So that makes these weights smaller. And if they're smaller, then you need a lot more input to basically produce an output, because you need to get past that threshold in the rectified linear unit. But the second one is the dropout. And dropout is a little bit fascinating. Like, it's not really clear why it works. So what happens basically, I mean, like, I guess people know why it works, because it does a similar thing like this does, but and so this modifies your loss function. So for this one you need to change your loss function. For this one you don't need to change your loss function at all. And so what this does is nothing but the following. So during training you get an input and you want to reconstruct that, right? And then you calculate the error at the end and then back propagate through. So what you do with a dropout layer, and you kind of like put this dropout layer in here, right? So this is the dropout layer. And what this does is it randomizes within the layer what to let through and what to cancel out to make zero. And it's completely random. Like it's fully, like it's connected to each of these neurons, and every one of them is just connected to like one of the things in there, and then each neuron in the dropout layer is connected to all of these, right? And so what it does, it basically is just, and you can say like drop out 50%, or drop out, and I think in that MNIST example for Keras.js, they have 50% dropout. So you randomly take whatever these produce, these hidden neurons produce, and you switch off 50% of it, randomly. I think you just switch off some.
It's basically you add noise. Why does
No, you don't really add noise. You remove knowledge. You remove its ability to like so. Well, what you also enforce is that every neuron now has to kind of like work on itself. Like it doesn't learn these clicks anymore. Like because you know when this one's on, or when like sometimes you have these dynamics where multiple neurons learn some similar stuff. And so you kind of force every neuron to learn for itself, and you switch off 50% or like 70% sometimes, maybe 10% if you. And then that way, you basically avoid overfitting on these networks.
So you don't overload.
Because you always switch off a different 50%, or a different 70%, or whatever.
Okay.
So, but don't even try to find the theory for why this works.
It just a lot of this. I've noticed a lot of the deep learning stuff is
it's you know, like in the end, deep learning is well, it's probably like a craft, I would say. Like it's not art or theory. Like you have a toolbox and you just try out stuff.
Yeah.
I mean, there are other things too, right? Like, so there are networks. So like sometimes you have really deep neural networks, and it goes on, right? And if you want to learn 70 or 80 layers, again, like even with your rectified linear units and like your adapted learning, you never really have any like proper error that back propagates anymore. And so sometimes like what people do is like they jump over layers, and so you can basically like, call these connections like autobahn or freeway kind of connections, like where data just gets like pushed through without changing it. So like similar stuff is happening in these what's it called, ResNets, or yes, so where you basically have the following structure. You process something, but then you also like circumvent that process and connect whatever this network does with the input again. So
that's not similar to LSTM?
No, because these don't have to be recurrent. It
seems
There's
like
a lot of
some
stuff.
things are coming from neuroscience, like the dropout I can see coming from neuroscience, because that's the idea of injury and stuff when the brain rewires.
Plasticity?
Maybe neuroplasticity or something, you know, but not necessarily just neuroplasticity is in a daily sense. But what I'm thinking is,
Like with
you know
injury?
how, with injury.
I think that could also be argued that it's
Plasticity, yeah, for sure. But I'm thinking
But
like
it's
something
also
that's
like,
radical more on that side than on side of daily neuroplasticity we
Oh,
have
yeah,
from
yeah.
learning stuff.
but you also have like this redundancy. So if
Yeah.
like, if you get hit in the head, you don't forget like one item. Like it's
Yeah,
distributed.
yeah. Unless you hit really well.
If you get hit
If
really
you wipe
hard,
out an
yeah.
entire region.
Yeah.
But yeah, so you have redundancy and stuff like that. But I think the dropout is just like
Fitness test.
a smart. Well, but during testing, you never drop out anything. You only drop out during training.
Oh, okay.
Yeah. Like that's so dropouts. It's just active during testing, during training, never during testing. Yeah, so these inception
And
networks,
so
they
what
have
is the-
these ResNet connections, I think.
And what are the dense layers?
Dense layers are just normal MLP layers. Yeah, I think these have these connections where like some of them get convolved multiple times and some of them just don't get convolved at all, and then you merge them. So that's kind of like this inception or ResNet kind of idea.
So that's the architecture we receive from there,
This thing.
is this whole thing, right?
I
is-
still believe you don't need a network that has I don't know how many layers.
Wow, that's a lot.
This is designed by architects, I
That's
can
a
tell you. They
Who
did
needs
not know
this?
when to stop. They don't really know what is going on, but it looks good.
No.
Yeah.
This is who needs this, right? So, like previously, like when I started this thing, and I was like, wait, like it's loading for a while, and I was like, why does it load for such a long
Now
time?
you know. Now you know.
I know why.
Yeah.
Because it's dumb. Yes. I mean, this is a joke, right?
No,
I
no.
don't think nobody
I'm
really-
telling you, this is how architects operate. We don't
Nobody
really know,
needs
but it
this.
kind of looks good, so hey, let's build some more.
Alright, so yeah, on Monday, I guess it was, we talked about LSTMs and basically, there's actually a couple of things that a couple of points that I got from this blog post. It's basically the unreasonable strength or power of LSTM, so that it's kind of like something
Okay.
to read also over the weekend if you're interested. So yeah, LSTMs are recurrent neural networks. So there's like we talked about the fact that there's like this state of the cells, which is so to say the memory state. If there's no memory, or if like the connection weights between the cell state and the input here is zero, like, well, then it's not a recurrent neural network and the memory falls away. And so in these recurrent neural networks, you kind of keep your memory over time, and as we had in one of our previous lectures, you can consider this like temporal idea as like basically copying your network over and over and over again, so that you don't have to worry about like this recurrent structure, but you basically just have like an unfolding of your network until a certain length. And so actually also interesting, like if you ever wonder how you like learn these networks with, for example, TensorFlow or some other neural toolbox. And what you need to do basically is you build these so-called tensors, and I guess I think Li Sheng might have talked about this. And a tensor is just like basically going from a scalar, which is just a number, to a vector, which is like either a series of numbers in a column or in a row, to a matrix. And then the next one is a cube, right? So, but that all like, and so you basically have a three-dimensional matrix, and then you could have a four-dimensional matrix, and so on. And all of these, like vector, scalar, vector, matrix, this three-dimensional matrix thing, these are all called tensors. And tensor is just the mathematical term for it. And so what you usually do to feed your data into these LSTMs is most of the time you'll have a three-dimensional tensor that goes in. Mostly, in most cases, if you have, I think in TensorFlow they call it either time major or time minor. In the first dimension you have the batch size, which is like I think the way we use it in my group. So basically each of these rows here that are matrices now is one sequence of data, right? And you have batch size many sequences. And so you have this dimension here as the sequence length, and then this dimension here as the input size. And so you can already see, so this dimension in that cube basically is your x, right? This dimension here is not seen here at all, because what you would need to do is like take this network and copy it multiple times down here. So this is the batch, and then the sequence length is basically what you need to do, which is from 0 to t. Okay, and in TensorFlow you have to define a sequence length, and all of them work like that. You have to define the maximum length of your sequences. Okay, and so this is how they work, and like basically in your GPU then you would unfold your network that many times, and then it learns through that. Okay, so it's never like that there's like a dynamic way that you can actually like adjust that. And so for example, if you use Keras, every sequence must have the same length. Okay? But in TensorFlow you don't necessarily need that. You can have different sequence lengths in TensorFlow, for example. That's one of the reasons why we're using TensorFlow and not Keras. And so what happens basically is for TensorFlow you have to define for each item like basically what the length is. And so what you build is kind of like this blackout kind of matrix that cancels out or adds zeros in your batch, and so all of them have like but still, the tensor is still the same size, but it's just padded with zeros. And then you have an additional vector that has, again, batch size, many entries, and that one's basically reporting to the network how long each of these sequences are in the batch, okay? So that's one way to do that. So that's, I think that one's called sequence length as well, or something like that. Yeah, and sometimes if you have like equal length for all sequences, you don't need to add this, and you just fill them in. But yeah, so that's kind of like something to consider. And in the GPU, because it's a lot easier to do, it still unfolds the network all the way, but then it just ignores what happens afterwards, okay? Because it will get zeros as input. All right, so that's just kind of like one thing to think of. That's like one of the major things that you need to change in your thought process when you're using these deep learning and toolboxes that work on tensors. The tensor flow, tensors are being like pushed through the network. That's what they flow through the neural network or the deep learning thing. Okay, so yeah, and LSTMs, they're really good at like trying to identify these long-term kind of relationships. We talked about how complex they are, so this is like a standard recurrent neural network. And they have these additional layers here, these sigmoid layers, which are basically like gatekeepers that allow information to flow or pass or not. And so that's kind of like their main purpose. And you can control this quite well, and that also helps you like maintaining the knowledge or maintaining the memory over longer time periods rather than over usually very short periods. We talked about like how all these fit together and what they're all doing, and then we talked about shortcomings and really like capabilities. I hope everybody tried this out at home and thought about like how, you know, like how can I trick the network and how can I cheat it. Then we talked about how like these LSTMs can be used within different types of applications. One-to-many, if you want to generate, for example, sentences, as one of the examples that I showed you from our group. Sometimes you want to just label one sequence with a certain class label, so you want to like identify the sentiment of like an input sentence. Maybe you want to translate something with many-to-many, or you want to basically model the language and try to predict what's going to be the next word. You would use these many-to-many connections. Talked about how this can be considered in like a small example where your dictionary is literally just 4 different characters, and that you're able to basically produce these kind of funky words or like these funky texts, and what this should illustrate kind of is that when you look at Paul Graham's language, it is very different from what it produces here for Shakespeare, and the difference basically is that these LSTMs, whatever data they get, right, like they will adapt to that data. So what they will do is kind of like learn the statistical distribution of your data within like the corpus that you're giving it. So you can literally learn different styles in your networks. And one of the ideas, like and learning these different styles, was kind of like the idea that we had here to maybe be able to switch the style of output depending on the affect that you want to convey or that you want to produce. We used quite a big data set, and I think this is probably what you need to do this. And we're not saying that our work is perfect or our affect-LM is perfect, but it produces some meaningful, some funny sounding sometimes sentences that are like meaningful in the sense that you can see, okay, there's a question, why did you have a best friend? Why did you miss your feelings? I don't know how that makes any sense, but why did you worry about fear factor? Why did you believe in divorce? I don't know, like these are kind of interesting questions that are being produced, but what this should illustrate is that it is possible to kind of switch these outputs quite a bit with like an additional input parameters that will help you or allow you to learn these connections or these different styles. We talked about how we can evaluate this, and we used Mechanical Turk. People that were reading these stories or these utterances, they had to rate how grammatically correct or sad or negative, etc. These responses were, and we found quite good results here, and like, I'm really happy about this. Also, the grammatical correctness was important for us because we didn't want to like have the network deteriorate too much from like the baseline, and we only see a drop after like increasing the affective strength way too much, where the outputs of the produced, like the network outputs will only be like happy, happy, happy and stuff like that. Okay. One of the other things that you can see here as well is the two emotions that deteriorate the quickest are anxious and sad. And if you look at our data set, you'll see that these words are actually a lot sparser than, for example, happy and angry language. So the more data you have on these topics, the better your predictions probably will be. So it's all like, it always kind of stands and falls with the type or the amount of data that you use in your models. We also saw that like we can improve the prediction of what's the next word going to be. These numbers are so-called perplexity numbers, which are basically a measure of like how certain the network is about its outputs and how correct it is. So it's like perplexity, I think, is defined as 2 to the power of entropy. So if you have the entropy of your output, you basically put that in, and you get like the certainty levels of your language model through that. And so the affect LM also learns to represent, to embed words with different affective contexts, and what you can see basically are that there's a clear opposition between negative emotions that are kind of clustered down here and positive emotions that are clustered up there. And one reason for why the negative emotions are clustered is because we only have, so we have our context, our emotional context that goes into the network that you saw here. So this part here, the emotional context, the E value there, that is encoded like this. So we have 5 dimensions. And this is positive emotion, this is negative emotion, this is angry, sad, and anxiety. And for positive emotion, it's a 1 hot vector, so you have 1 here and 0, 0, 0, 0 here, right? But for negative emotion, you would say it's a negative emotion, but then in the negative emotion it was sad. So you have 2 entries that are 1 instead of like just 1. So that there's kind of like this hierarchical coding scheme in Luke, which is basically like this. I can show you this. Like, is the camera off?
Oh, yeah, sure.
Is it up?
No,